Okay, so angular momentum is conserved because there's no additional net torque acting upon the comet. So we know that net torque is equal to F cross R, but because your only force is Fg and it's already parallel to your lever arm, it should generate no net torque. And then we know that change in momentum is equal to net torque times time. But because you generate no net torque, there's no change in angular momentum. So angular momentum is conserved. And then the equation for it is angular momentum of para G is equal to angular momentum of apogee. And then we know that it is the inertia times angular velocity. So this angular velocity of para G. And then angular velocity of apogee, right? And then our span on it. So we'll treat this as a point mass. So your C is just 1. Same comment. And then R square. And then we'll look at para G. So it will be distance of R para G away. And then we know that V is equal to omega R. And so omega is equal to V over R. Right? So replace omega with that. So omega para G can be turned into linear velocity of para G over R para G, right? And then the same thing for apogee. Same comment. The distance R apogee away. And then mass cancel out. Then one of the R cancel out on both sides, which leave you with this equation. Okay, mechanical energy is conserved because this is like a closed system with no like external force like friction or any thrust from the thruster. So we can assume that energy remain constant in this closed system, right? And then the equation is energy of apogee is equal to the energy E total of perigee. So E total is just K plus U, right? Then K is equal to 1 over 2 mv squared. Then U is equal to negative constant G, mass of stationary, mass of the orbiting object over the distance from the stationary to the orbiting object, right? So expand on what we got. So 1 over 2 mv of apogee square minus mass of the sun, and then just m for mass of the object, or all over r apogee. Just move this over. Then 1 over 2 ke of perigee vp square minus g mass of the sun, mass of the object, all over rp. And then all of the mass of the object cancel out, leaving you with this equation: 1 over 2 v apogee square minus g m of the sun over ra is equal to 1 over 2 v a v 1 over 2 v perigee square minus G mass of the sun over R perg. Okay, so for part C, we have to prove that equation right there, and I have already rewrite what we found in part A and part B, so we use this to prove part C. Okay, so first we'll try to find VB, so V per G square minus GMS over R per G is equal to 1 over 2 VA square minus GMS over M of the sun over R apogee, right? So I'll move off the velocity to one side, and so off the KE to one side, and off the potential energy to the other side. Then I'll factor out common terms. Like on the left side, you can factor out the 1/2. And then on the right side, you can factor out constant G and then the mass of the sun. So on the left side, we have this thing right here, and this is a difference of square. So technically it's just A minus B times A plus B, right? Which is equal to A squared minus B squared. So I can just factor it out. So this is just V per G minus V apogee times V per G plus V apogee, right? Mass of the sun. And then I'll do cross multiply to get common denominator, which should produce RA minus RP over RP RA, right? But then in our equation from part C, there's no RP, so we have to find a way to get rid of it. So using the equation we found in part A, we can, so this is it. So R per G, V per G is equal to R apogee, V apogee. You can divide both sides by V per G to get this equation. Right? Have this equation to plug it in. So the new equation is so RA minus R apogee V apogee over V per G all over R per G R apogee, right? And then I'll simplify it further. Right, just multiply the RA with VP over VP to get the common denominator. So you have VP RA minus RA VA all over VP. Then that divided by RP RA, right? R per G R apogee. So now from what we found, you can factor out common denominator, factor out common term. So you can factor out R apogee. Okay. So now VP minus VA would cancel out with the one on the left side. This RA would cancel out with the other R apogee, which leave you with this equation. I'll factor the left side. Actually, no, I'll keep it. So you have 1 over 2 VP plus VA is equal to GMS over VP RP. Then multiply both sides by 2. So VP plus VA is equal to 2 GMS over VP RP. Then minus VA. So you get VP is equal to 2 GMS, mass of the sun, VP RP minus VA, right? But then in the equation, the denominator is VARA. So we know that VPRP is equal to VARA. So we can just replace the denominator with that. So the final equation is V para G is equal to 2 constant G mass of the sun over V apogee R apogee minus V apogee. And that should match. So earlier we proved this equation right here. V para G is equal to 2G mass of the sun over R apogee V apogee minus VA, right? But then we cannot use this to find any of the speed because there's two unknown in it. This V apogee and V para-G. So we can replace V para-G with this equation right here. So we know that V para-G, R para-G is equal to V apogee, R apogee, right? So V para-G is equal to V apogee, R apogee over R para-G. So we can replace it with that. There we go. And then I'll add both sides with VA. Right. So V apogee, R apogee over RP plus V apogee is equal to this. Okay. And then multiply top and bottom of VA with RP over RP to get common denominator. Right. So I get VA RA plus VA RP all over RP. R per G is equal to 2G MS over RAVA. Okay. Okay, then I'll factor out VA. So VA, V apogee is times R apogee plus R per G over R per G is equal to this. Move off the V apogee to one side, so multiply both sides by VA. Right. So I get VA square, then R apogee plus R para-G over R para-G is equal to 2G mass of the sun over RA. So I'll multiply both sides by R pair G and divide by R apogee plus R pair G. Right. So you get this 2G M sun, and then R pair G all over RA, then R apogee plus R pair G. Then divide both square root both sides, right? So VA is equal to that, okay? Then I'll plug in all the numbers. G is a constant. And then mass of the sun is 2 times 10 to the 30. Then the distance of the perigee is 6.1 times 10 to the 11 all over distance of apogee is 6.1 e to the 10, no, e to the 11 times, wait, the distance of perigee is 5.1 e to the 10. Okay, now our apogee is the same thing, 6.1 e to the 11 plus the distance of perigee, which is 5.1 e to the 10, which should give you 5809 meter per second, right? Then to find V perigee, okay, earlier we found V apogee, now to find V perigee, we use this equation. So VP is equal to, and then V apogee is 5809. Then distance of R apogee is 6.1 e to the 11 all over distance of perigee, which is 5.1 e to the 10, which should give you 69481 meter per second, right? Perigee should be. So first I'll find E total for the apogee. So we know that E total of apogee is equal to K of apogee plus U of apogee, right? And K is just 1/2 mv squared. Then U is negative G, mass of the sun, mass of the object, over the distance R between the object and the stationary mass, center to object. So I'll replace it here. So 1/2 m comet VA square, V apogee square minus G, mass of the sun, mass of the object, over distance R apogee away. And then last, in the previous problem, we found that VA is equal to radical 2G ms RP, R perigee over R apogee, parentheses, R apogee plus R perigee, right? So just square both sides. So we get VA square is equal to the same thing, but without the square root. Right, so I'll plug it into here. So I get 1/2 m and then 2G G mass of the sun RP all over RA parentheses R apogee plus R perigee, okay? Minus this there. And then to get common denominator, I'll multiply the potential energy with RA plus RB on top and bottom, which is just 1. Right? So I get this new equation, and then the 2 cancel out with each other. So I get this new equation. G, mass of the sun, mass of the object, RP over RA plus RA plus RP per G minus MSM RA plus RP all over RA and then R apogee plus R perigee, right? Then I'll combine them. All over this. And then apogee plus R perigee. There. So you have this equation. Then I'll distribute the right side. Minus RA minus G M mass of sun mass RP all over R apogee and then R apogee plus R perigee. Okay. So this 2 would cancel out, leaving you with this. Right. So you have this. And then the R apogee would cancel out. So you get negative G ms mass of the object over RA plus RP. And then we know that RA plus RP is just the major axis. So that is just twice of the semi-major axis, which is A, right? So A in this case represents the semi-major axis. So if you have the whole major axis, it's just 2 times that of the semi-major axis, which is how I got this equation right here. And then we need to find V, the elliptical speed. So I'll rewrite the E total equation. So in this case, K, and this is equal to E total, by the way, of an ellipse. So K plus U is equal to whatever we found, right? To this. And then we know that K is 1 over 2 mv squared plus or minus G mass of the sun, mass of the object over R, right? Whatever the distance R is from one of the foci is equal to this for an ellipse, right? And then I'll move the potential energy to the other side. So I get this equation. Right. So I'll move this to a new page. So copy it. Right, so I have this equation right now. So I'll multiply everything by 2. So multiply by 2 and then multiply the right side by 2 to get rid of the half and all. So I get mv squared is equal to negative gms m over a, the semi-major axis, plus 2g mass of the sun, mass of the object over r, right? Then all of the mass of the object can cancel out, which leave you with v squared is equal to negative g ms over a semi-major axis plus 2g mass of the sun over r, distant waves from wherever the comet is. Factor out common term like the g mass of the sun. Which give you 2 over r minus 1 over a. Then square root both sides. So your final equation is this. Which should match up with the required one. Earlier we found the v for an ellipse is equal to radical g mass of the sun 2 over r, but in this case it's rp, right? Because that's what it's asking for, minus 1 over the semi-major axis, right? Then for v orb, we know that in a circular motion orbit, fg is equal to fc. So this is g mass of the stationary, or the sun in this case, and then mass of the object over r squared, the distance from center of the stationary to the object, is equal to mv squared over r. Same thing here. So one of the r cancel out, right? Mass of the object cancel out. So you get v squared is equal to g mass of the sun over r. Then square root both sides, which give you v orb to be radical g mass of the sun over r, right? But then in this case, your r is your rp, right? So I'll just rewrite that. So v orb is equal to radical g ms over rp. Okay, so to determine which velocity is faster, we have to look at the parenthesis, right? So I'll just factor out this real quick. Right. So in a V ellipse, we have 2 over rp minus 1 over the semi-major axis. And then in a V orb, we have 1 over rp, right? Because g mass of the sun is the same. So we have to determine which one is greater, and therefore it will produce a greater speed, right? So the one for the ellipse should be greater than the one for V orb, because okay, let me split it up. So 2 over rp is 1 over rp r per g plus 1 over r per g minus 1 over a, right? And then this. But then we know that 1 over r per g should be greater than 1 over the semi-major axis, right? Because the distance of the perigee is not even halfway of the semi-major axis. So if we have 1 over a number, right? So this is rp minus 1 over a, right? Bigger number. So this is your semi-major axis. You would still get a positive number, right? So if we have 1 over rp plus a positive number right here, it should be greater than 1 over RP, right? So therefore we know that V ellipse is greater than V or